All right. An electron in JJ Thomson's E over M apparatus moves perpendicular to a B field. So we've got our B field into the page, say, and we have an electron moving this way. And now using our right-hand rule, our force is QV cross B. And remember, for our right-hand rule, we have to put our fingers in the direction of positive current flow or positive direction. Or we just need to invert it. So if we put our fingers in the direction of the velocity, our palm in the in the direction of the B field, then our force is in our thumb is pointing in our force direction. But in this case, because we're talking about an electron, we have to invert the force, so the force is actually going to be downward. So not according to right-hand rule, but that's because Q is minus E. Okay, so for an electron, we have to point the force in the opposite direction. Okay, that's not super necessary for this question, but just an aside. So our force is QV cross B, which, as they're perpendicular, can be just written as QVB. So it's moving currently, it initially is moving with a radius of 10.4 centimeters. So this is our centripetal force, so mv squared over r. And so we can readily solve this for our velocity. And then, so what we have, and then we add an E field and it makes the path straight. So we've got it moving in some circular path, and then we add an E field, which in retrospect, I'd have to make the E field this way, which makes the path of the electron straight, as the B field is going to want to continue to make it go in a circular motion, but the E field is going to oppose it. So that's a magnetic force, while our electric force is just QE. All right, and so for it to fly straight, our QVB minus our QE must equal 0. As for it to fly straight, there's no longer centripetal acceleration, or QVB is equal to QE, or our, what is the value of B? So B is E over V. Okay. So our velocity, we can use this above expression to solve for our velocity. So cancel the V here. Our velocity is just QBR over M. And so then our B field is just E over Q BR over M, which we can bring this B over to this side and say B squared is ME over QR. And so then we're given our radius, we're given it's an electron, and we're given that the E field, and we're given the E field. In this case, we've already kind of taken into account the charge on the electron in all of this. Or at least here we have actually. So in retrospect, I should have written this as E and E here, not Q. And so in retrospect, this should have been E. Not that it makes a whole lot of difference, but we would end up with a negative in our square root, which wouldn't be so kind. And so then B squared is our mass for an electron, 9.11 times 10 to the minus 31 kilograms, times our E field, which is 18.10 times 10 to the 3. And a volt per meter is just a Newton per Coulomb. But I might as well, I guess, leave it in volt per meter. I don't know why I converted it. Charge an electron is 1.6022 times 10 to the minus 19 coulombs. And the radius was given as 10.4 centimeters, so 0.1040 meters. And so our B is actually the square root of all of these. And so our B is 9.948 times 10 to the minus 4. And if we do work out the units there, it will be Tesla. And so that's our B field. And so suppose our E field measurement has an uncertainty of 0.750 kilovolts per meter, and our radius has an uncertainty of 0.1. What is the total uncertainty associated with the B field? Okay, so if we represent our B field as, or if we represent our B squared as ME over ER, and our mass and our electric charge don't have any uncertainty, then we can compute our uncertainty through just differentials. So this will give us 2B dB is equal to M dE over ER plus ME over ER squared del R. Where although the derivative of 1 over R would be minus 1 over R squared, the del R is plus or minus. So we're obviously going to take whichever will give us the larger error, as we want to know our maximum uncertainty here. But B squared is, so in this case, B squared is ME over ER, or E is, how to write this, ER B squared over M, or ER over M is E over B squared. So we can put that in there, and in fact we can also use that over here. So we see that we have, so this is just B over R, and this is just b squared over e. Okay. And so then, oh, sorry, this is b squared over r. There you go. That makes more sense. Okay. So then we have 2b del b is b del e over e plus b squared del r over r, dividing through by b squared, or sorry, dividing through by the 2b on this side. Then our del b is just b over 2 times del e over e plus b over 2 del r over r. And so then we have our b field, which is just, so 1/2. Our b field was calculated as 9.948 times 10 to the minus 4 Tesla. Our error in our E field is given as 750, just 750 volts per meter, so it's 0.750 kilovolts, but I just converted it over 18.10 times 10 to the 3 volts per meter. And our uncertainty is given as 0.1 centimeters, so 0.001 meters over 0.104 meters. And if we do this out, it comes to 2.539 times 10 to the minus 5 Tesla. Okay. And, okay, so now checking through our solution here. So our B field comes out to be 9.948 times 10 to the minus 4, so it's, or 0.9 times 10 to the minus 3, so that's the same. The last digit is a little different, but that would just be rounding differences. And the uncertainty in our field comes out to be significantly different. Oh, but they have a different B field here. That's kind of odd. Yeah, they use a different B field for this calculation, so that's just odd. I don't know why that would be the case. Did the question give it? Nope. So I have nothing there for why that would be the case. So in any case, that's the reason why that's going to be different. And this is just the solution. Oh, here it is down here, 2.54. Yeah, so okay. So it is the same. They just, in their summary, gave a different one for some reason. Okay, so that looks good. All right, so that looks good.